Hello class, I'm talking to you tonight about problem 1.13 in homework assignment number 1. And in this problem we've got a stream with a wastewater treatment plant shown here in red, an upstream inflow and a downstream outflow. This is a problem that are referred to as end member mixing problems. And what we want to do is conceptualize this problem as having a well-mixed box represented in the orange square that you're seeing now, with two inputs that mix together completely and yield one output. And to solve this problem, we'll apply the continuity equation across that box, meaning that the sum of the inputs is equal to the sum of the outputs. Mass is neither created nor destroyed. We don't have any indication that mass is stored within this box. So for both water and the dissolved constituent, inputs must equal outputs. Now what does that mean to us in more practical terms? Well, for water, inflows have to equal outflows. So you might conceptualize this as a bathtub that's got inputs from both a shower head and a faucet and one output out the drain. If that bathtub's at steady state, the sum of the ins must equal the sum of the outs. Now, for our purposes, we can look at that using discharges, represented here with Q's. So QA plus QB must equal QC. We can apply the same kind of analysis for the dissolved constituent in these cases. So for our solutes, we see that the sum of the inflows must equal the sum of the outflows. Now, we can represent those loads as a discharge multiplied by a concentration. So QACA plus QBCB must equal QC concentration of C. Using the two equations that I've boxed here, you can solve for up to two unknowns. In your homework problem, those two unknowns are represented by two of the discharges, though in other applications you may know the discharges and be asked to solve for a concentration. And as a reminder, this is what we call end member mixing, meaning we take two distinct end member inputs and mix them together to create their discharge weighted output from a system.